Alright guys, here we go. Second lesson of chapter 2, getting into power functions, direct variation, inverse variation, all those fun things. So a couple things I made note of here that I want to go through with you first before we get into those notes. So I'm looking at page 169 in the textbook. Let me go to that real quick. So here we go. So our power functions, our general form is going to look like this, where A is obviously the power or the exponent, X is the base, and K represents what they call the constant of variation. In a second here, we're going to talk about direct and inverse variation. There's always some value that can go in front. We saw that with quadratics in the last section, right? If you have ax squared, right, that a can be your constant of variation in that scenario that affects the stretching or shrinking of your parabola. So this is just another model for any general exponent. So when you were to look at some of these formulas, and at least a couple of these should be familiar to you, obviously circumference and area of a circle, a little physics here with force of gravity and Boyle's law. So as you look at circumference, so probably the best way to say this would be direct variation is whenever you are multiplying your constant, 2 pi, times the variable. So when it's multiplication, in these terms, we're thinking of direct variation. So we would say the circumference varies directly with the radius of the circle. The power is what you're seeing would be basically over the variable. So that would be r to the first. So they're calling that a first power. And the value in front of the in front of the variable, which is 2 pi, is the constant of variation. If we did the exact same thing with the area of a circle, we would say that the area varies directly with the square of its radius, since it's obviously the radius squared. And again, it's direct variation because it is our constant, which is pi, times the radius, times the variable. So obviously it's a power of 2. Our constant is pi. Down here is where we get into inverse variation. Inverse variation is where you are now doing the constant divided by the variable. So this will be inverse variation. Keep in mind, they see these whenever you put an exponent on bottom of a fraction, they're identifying that as a negative, because if you can remember your rules with exponents, when you did negative exponents, remember that a negative exponent caused a variable to go below the fraction bar. So you could write this as k times d to the negative second power, or if you want to make your exponent positive, you move it on bottom like they did, and now it's k divided by d squared, right? And so that's where they're identifying the exponent as a negative exponent, because now it's on bottom. So these, when you see the division, now we would read this as force varies inversely with the square of distance. Same thing down here for Boyle's law. This one is talking about volume and pressure. So we would say volume varies inversely with pressure, since pressure is on bottom. And again, those guys have the negative powers. The constant of variation would be the k that you see here. So that would just be a single value on top of the fraction. Let's see if we can do one on our own here. So in example 1, they were talking about the time of a pendulum. So you think of the pendulum swinging back and forth. They're saying that the time varies. Now on this one, it's a little tricky because they don't say direct or inverse. So one thing they want you to know is it's automatically direct if they don't say otherwise. So that's like the default word that we can throw in there if they don't put direct or inverse. So they could have said that time varies directly with the square root of the length. And so if we put that into terms of what we just saw up above, we could say time. So time is a function of length. So time varies directly with the square root of the length. Okay, and so you could write it this way. If you want to put it as a 1/2 power instead of square root, that would be fine too. So the exponent would be 1/2 if you were asked that. Your constant is obviously k, and that would be that. So let me flip back over to the notes here. And get us into these. So here's a little more similar information. So now they're just asking us to analyze these guys in a couple different ways. It's saying state the power, the constant. They want us to graph it and analyze it. So a lot going on here. So just like we showed in the last one, the fourth root of x could also be written as x to the 1/4 power. So that would make our exponent 1/4. There's no number written here, so remember we always know there is an invisible 1 sitting in front of any variable. So that would be our constant of variation. If we wanted to graph it, at this point they're wanting us to graph these in our graphing calculator. So if you did graph this, you would see something like this. It's real similar to the square root function that we've already done. So as far as analyzing it, there is so many ways of analyzing a graph. There's just a ton of information we could give. So if they ever just say analyze it, throw in the most common things that you do recognize within a graph. But all of these are things that you should at least be familiar with because you could be asked for any of these. So domain, range, where is it increasing, maximums, minimums, asymptotes, those are all things that we've already talked about. So as long as you're at least familiar with those, so that if you're asked about those in a test question, want to make sure that we can come up with answers for those. One thing I wanted to mention is the end behavior, because this is always new at this level of math. The first chapter we will do in calculus later on in the year will be on limits. So I wanted you to see this notation. So this, we would say the limit of the fourth root of x as x approaches infinity is infinity. So what we're seeing is when they say as x approaches infinity, all that means is as your graph goes to the right. Right? So as my graph goes horizontally to the right, what is my graph doing vertically? So as I move to the right, my graph is going up. So that's why it's positive infinity. So this graph, even though it's kind of a flattening curve, it still increases forever. It goes up and up and up and up. So this is always moving left or right. This is always what is my graph doing up or down? Like what are we approaching as we go up or down? One more of those. Remember what we talked about, if your x to the third is on bottom, then that is the same thing as x to the negative third power. Right? So this is an inverse variation. Our exponent's -3. Our constant would be 1. And again, we could graph it with our calculator, and then a lot of ways, as we've already talked about, to analyze a graph like this. So I tried to highlight on one that I wanted to do with you the main things that I want to make sure you know how to state. So take a look at this one with me. It is -1/2 cube root x is the one that we're looking at right now. So let's throw that into our graphing calculator. So -1/, and I'm going to throw mine into fraction mode. I don't know if I've mentioned this in an earlier video or not, but anytime you have a fraction like this, if ever there's multiple items going on and you want to be careful as far as parentheses or whatever, the safe approach is to pull up the F1 menu and actually put your calculator into fraction mode. It's in green, so I'm going to hit the green button first. So alpha F1, and then that first item in the menu is fraction mode, so just hit enter, and now I can type it in. So I got my -1 on top, I got my 2 cube root x on bottom. Go ahead and graph that. The domain you could already answer. You don't need to look at a graph to analyze domain. We should already know that my domain is everything except 0, since I can't have 0 on bottom of the fraction. So we already know the domain. The range, you can see based on the graph that my range would go up and down forever except at 0. Right? So again, just like the domain, you would write the range the same way. -infinity to 0 with parentheses, and union with 0 to infinity. So the range is going up and down forever. The asymptotes, so you can see my vertical asymptote is x equals 0. My horizontal asymptote is y equals 0. As far as a max or min goes, since this graph approaches infinity forever, there is no local max. We would simply say its maximum is that it approaches infinity, positive infinity, and the minimum approaches negative infinity. It's because it's infinity. Infinity is obviously not like a number you can land on, so we really more like state it as a value that you are approaching in cases like that. End behavior on these guys. Two things we could look at for end behavior. We can talk about the end behavior as we go to the left. We can talk about end behavior as we go to the right. So if we were to say something like the limit of our function, which is all of this, I'm just going to say f of x so that I don't have to rewrite all of that. So the limit of our function as x approaches negative infinity, in other words, as I move to the left, what is my graph approaching? So as I move to the left, you see that my graph is getting closer and closer and closer to 0. So that's the limit that we are approaching as we move to the left. How about as we approach positive infinity? So the limit of our function as x approaches positive infinity, or as we go to the right, is also approaching 0. So that's how we could describe the end behavior. So let me flip over to this guy. I'm going to take you back to our book for something really quick. On page 170, there's something I want you to see. So simply, just wanted to remind you of a monomial function. Simply means a function that has one term. So remember, mono means one, so a one-term function. Functions are always separated by pluses or minuses. I'm sorry, terms are separated by pluses or minuses. So if it's just something x to the something, it's just a single term. And so we call that a monomial function, which we're going to be looking at here. I also want to show you real quick, and I know you've seen this before, but I'm going to remind you of what our x to the third function looks like, because that's going to come up in our next example right here. Let's see if I can zoom, make this a little more clear for you as much as I can. So what they're wanting us to do is, if I had 3x to the third, how do we obtain that graph? So they want us to consider what is basically the parent function, which would just be x to the third. So how would I affect x to the third in order to graph a graph like this? So we're just going to do a little fill in the blank here, so we didn't have to write all this out. So we obtain the graph of 3x to the third by multiplying the graph of x to the third by a factor of 3. Right, that's what we're multiplying by, is 3. Both are odd functions, so how would we sketch it? If I had x to the third, so again, you should already be familiar with a parent function for x to the third. It would be the one that looks like this. So this is our x to the third graph right there. So how would I have figured out that this is sort of the new graph that I would sketch by multiplying by a factor of 3? Well, as we talked about earlier, that factor of 3, because it's a number bigger than 1, would cause a vertical stretch. Or you could describe it as a horizontal shrink of a third. So you could look at it that way as well. But if we described it as a vertical stretch, remember that's going to cause your graph to get skinnier and skinnier, right? Because the same point that would have been here is now up here, right? It's being stretched vertically. You can always check these like they want us to on here by graphing both. So if I did x to the third, that'll be the first graph that comes up, and then the red one is going to be 3x to the third. So let's take a look and make sure we got this right. So this blue graph is going to be our x to the third, and then the skinnier red graph is our 3x to the third because of that vertical stretch. So using that information, we could come up with some sketches as long as we're familiar with the parent function, and that's kind of a big deal. So how about the next one? So we got the negative 0.5 x to the fourth. So in this one, we obtain the graph of this by doing what to x to the fourth, right? So again, we are multiplying by a factor of 0.5, and then reflecting it, and I'm not going to fit all this in there, but I'll abbreviate, and then reflecting it across the x-axis. computer type is much smaller than my handwriting. So, so both are even functions. Again, if we are familiar with x to the fourth, powers of 4 can be a little tricky. In its most basic raw form, it really looks like a squished parabola. Your x squared, and actually let me just do this while I'm thinking about it. I'm going to show you the comparison. It's very similar to x squared, but it's kind of a flattened version of x squared. So you guys all know what x squared looks like, our basic quadratic that looks like this. When you go x to the fourth, as you start increasing your exponent with even powers, it sort of flattens the curve. So x to the fourth, so you can see the comparison here. If you zoom in on this, you're going to see that the red graph isn't quite so much of a curve. It's a little more squished and flat as you go through 0. Right? It's a much flatter bottom to it. So that is x to the fourth. As you start putting more and more terms into x to the fourth, eventually it starts looking like a W. But for now, we're just looking at x to the fourth, which would be this graph right here. So what would this 0.5 do to that graph? Right? So this would be our vertical shrink, right? Or you could describe it as a horizontal stretch. But essentially it's taking our x to the fourth, and it's not only reflecting it because of the negative, but it's also making it wider and flatter. Okay, and so that's how we could at least sketch this graph just based on our knowledge of what x to the fourth looks like. Okay. Take you back to something in your book really quick before we fill in example 4. So this is at the bottom of page 172. I wanted to summarize a little bit graphs with power functions. And a lot of this you've already seen before, but if nothing else, it's great reminders as we're kind of putting a lot of information together right now. So let me pull this over to here. So if you look at these 4 graphs that you're seeing, so a lot of what's going on here is dependent upon the exponent itself. So here's our model that we're looking at right here. So something times x to the a power. So anytime your a value is negative, so if we have a negative exponent, that gives us this decreasing graph that we would see right here. You've run into these before when you did growth and decay. This is our decay graph versus the positive one where it's our growth graph. But anyway, they all run through a certain point, right? So the point that we want to recognize, that they want us to recognize, is if I plug in a 1 for x, then k, the constant of variation, would be my y value. So that's a point they want us to always recognize for any graph. Okay, and so we have that. So anytime a is positive, we get the red growth curve that you see right here, our increasing graph. Obviously, if our power is 1, it's just a linear function. So that's the black one. And then the blue one that you see, which should look familiar to you, is anytime you have the exponent between 0 and 1. So we've already done this with like x to the 1/2 power. Remember, x to the 1/2 power is the same thing as the square root of x. Right? That was one of your Algebra 2 ideas, right, with fraction exponents. Let me say that again. So x to the 1/2 is the same thing as the square root of x. So that would give you a 1/2 power in this little range right here, and that's what's causing this type of a curve, and we've already seen those before. If you do put a negative in front for k, they get the reflection that looks like this. And so we're going to put a few things together here and do one of our own. And again, I'm trying to make some of these fill in the blanks so you don't have to write as much. So hopefully you're printing these out and filling it out with me. But we're going to look at this graph right here. So we're going to see if we can't use all that information and actually come up with a graph, our own sketch of a graph like this, 3x to the negative third. So there's several things they want us to identify in here. That's what we're going to go through right here and fill in the blank. So our k value is 3. That's our constant of variation. It's positive. Our a value, our exponent, is negative 3. And so therefore, what would the graph pass through? So if I plugged in a 1 for x, then 3, my k value, would be my y coordinate. So it's going to go through the point 1, 3. and is, and here's a new vocab word for you, asymptotic to both axes. And all that means is the x-axis and the y-axis are both asymptotes. That's all that means. They asked us to describe this. So the graph in this case would be odd. Oh, I'll get to that here. The graph is decreasing in the first quadrant. Decreasing in the first quadrant because of this guy, right? And because this is positive, right? If this guy were negative, then we would be in the fourth quadrant. So just keep in mind that's what this guy was. So if your k is positive, you're in quadrant 1. If k is negative, you're in quadrant 4. That's what those are telling you. So, and then the function is odd was the last thing they wanted us to state, because if I replace x with negative x, then the entire result of the function changes signs and becomes negative. I want you to keep something in mind, because we're going to sketch this on our own right now, and just based on this information, see if we can't come up with a good sketch. So you can see kind of how this would be done. So we have a point 1, 3. And we just described a lot of information right here. So we know both asymptotes are the axes. So I have an asymptote here and an asymptote right there. So I got to fit within those asymptotes. I know it is decreasing in the first quadrant because of this. And so I can already sketch this curve based on that information. In order for this to be an odd function, right, that means I have to be able to flip this page 180 degrees, and I should be looking at the same graph I'm looking at now. I wouldn't if this is all I had. So how do we make it so that it's an odd function? Well, remember what this is telling you. This means that here's what you started with. When x becomes negative x, my y value becomes negative y. Which means if I had a point like 1, 3, that would become negative 1, negative 3. And remember, if I have an asymptote here as well as here, and in order for this to be an odd function, it would have to do something like this. Right? And so now we know we have an accurate graph. It fits this entire description that we just talked about. So there's a ton of information we can get based on what I see right here that would allow us to sketch a graph without a calculator. And so a lot of information there. So remember here, you can always check it, right? So if we plugged it in, here's what that graph would look like. If you ever want to check the points to make sure it's going through the same set of points that we just described here, you can always go into the table. So second table, and lo and behold, here's the negative 1, negative 3 that we talked about. Here's 1, 3, right? So we know we're on the right track with that graph. Let me talk you through part B as well. So this is negative 1 x to the 1.5 power. One thing that you do have to keep in mind on that is the same thing. So 1.5, if I can think of that as 3 over 2. One of the things you covered last year in Algebra 2 was fraction exponents. Remember that the top exponent is your power. The bottom exponent is a root. So that is the square root of negative x to the third power. So this is another way of looking at this. So kind of a couple of different ways we can see this in order to help us figure out what we need to figure out. So k is negative 1. That's our k value. So because that's negative and because a is greater than 1, they want us to know on this that the graph contains 0, 0, and I'll explain that in a sec, and passes through the point 1k. So remember for this one, We can always write 1k as a point that it would pass through. That's like a point we should always note. In this case, our k value was -1, so 1, -1 would be that point. So what's with the 0, 0 thing? If you look back at this page, you'll notice all the graphs pass through 0, 0 except the one that we just did. So when a is negative, we get the asymptotes. So that's why it does not pass through 0, 0 like the other ones do, right? And so that's something we got to make sure we're familiar with. Because our k value, our leading term, is negative, notice that we would now be in the fourth quadrant. So fourth quadrant when your k is negative, and it is decreasing. And the function f is undefined for x is less than 0 because of this. So let me take you back to this idea. Remember, this is a radical, right? So because it's a square root, with the square roots, I am limited on my graph as far as negatives go. So this guy is undefined for x is less than 0 because of the square root idea that I'm seeing right here. And just remember, it's simply decreasing because what would have been in the first quadrant, which would have been here, so it would have been growth and increasing, except the leading term was negative, so it caused it to reflect, and now it is decreasing. Okay, and so just if we were to go off that knowledge, again, we could kind of come up with a sketch like we did here. We know this one would be limited to the fourth quadrant because of this idea, right? And so again, we could come up with our own sketch just based on that information. So let me just show you this. Sorry, this is getting twisted up. So here's what that would look like, just based on that information. Okay. For the last one, I wanted you to try to sketch one on your own. So I wanted you to take a look at C on your own if you can from the last page. See if you can come up with the proper information and sketch it before I do. So at this point, I'd like you to pause the video, come up with your own sketch. This is the last thing that we're going to do, and we'll be done. So see if you can come up with your own sketch, and then I'm going to do it right behind you. So for part C, let me quickly flip back so you can see what it looks like. So it is negative x to the 0.8 power. Trying to get all that on the screen there for you. So here you go. This is what it looked like, negative x to the 0.8 power. So again, because my exponent's not negative, I know that it passes through 0, 0 as well as the point 1k. So those are always 2 points I should be able to put into this. So let me just throw those points in. So we had the 0, 0, 1, -1. So this one right here. All right, so keep in mind that because our leading term is negative, this was a reflection. So originally with a exponent of 0.8, that being a number between 0 and 1, we know we would have gotten this square root function that typically does this. It would look like this, but that was reflected. So now it's taking on this form because it reflected across the x-axis with that leading negative term. So it's kind of go forever that way. And then there's one more piece of this that you got to get is understand when there is more than just that first or fourth quadrant. And that's where the whole odd or even function comes in. So this one, if I replace x with negative x, nothing changes, which tells me it's an even function. And even functions reflect across the y-axis, which means I can also draw my curve heading this way as well. And so that would be our sketch if we were to try that on our own. But again, if we can kind of suck out all the information we can get out of this, it helps us come up with our own sketches. But that is it for this one.